Okay, let's dive right into this. We're looking at something really fascinating today, a bunch of scientific research papers. And hidden deep inside them, there's this strange pattern, almost like a ghost in the machine, that reveals something incredible about how modern science actually works.
Okay, so at the very heart of what we're looking at, we find this sentence. It's dense, right? Super technical. Something about mathematical, numerical, and algorithmic models for simulating combustion. Think rocket engines. It seems pretty standard for this kind of thing, but this is where our story really begins.
And there it is again, the exact same sentence, word for word. Maybe it's just a coincidence, right? Different papers, but similar topics. It could happen.
And
And again. Okay, this is officially getting weird. This exact phrase shows up dozens of times across completely different research papers. So what is this? Is it just a massive copy-paste error? Or is there something way more interesting going on here? This is the central mystery we are going to solve together. Because that repetitive, almost hypnotic sentence, it is not an error. It's a clue. In fact, it's the key to understanding one of the most powerful tools in all of science today. So let's start by treating this phrase not as a glitch, but as something else, maybe like a scientific mantra, a core idea that's so fundamental it just has to be repeated over and over. And to get it, we really have to break it down. So let's decode this thing. We're going to take this mantra apart, piece by piece, and reveal the powerful scientific engine that it's actually describing. So this is basically the three-step recipe for teaching a computer about the real world. First, scientists build a mathematical model. They take the laws of physics, like how heat moves or how fluids flow, and they write them down as equations. But computers, they don't speak pure math. So the second step is a numerical model, which translates those equations into numbers a computer can actually work with. And finally, the algorithmic model. That's the actual step-by-step set of instructions that tells a computer exactly how to crunch all those numbers to get a final result. A perfect example of this in action is a field called Computational Fluid Dynamics, or CFD for short, and it pops up all over the research we looked at. Using that exact same three-step process, engineers can simulate the flow of liquids and gases. We're talking the super hot exhaust from a rocket or the air flowing over a jet wing, and they can do it all inside a computer. So why go through all this trouble? Well, for the exact reason the mantra says, predictive capabilities and design insights. The whole goal is to build a kind of crystal ball out of code, to see how a design is going to work or fail before you ever spend a single dollar actually building it. In a way, this whole process creates an entirely new kind of laboratory. Yeah, a laboratory that exists completely inside a computer, a place where the only limits are the laws of physics themselves, not your budget, not safety concerns, not even scale. I mean, think about the old way of testing a new rocket engine. You have to physically build it, which is unbelievably expensive. Then you've got to ship it to some remote location. And the test itself is slow and, frankly, extremely dangerous. Now compare that to computational modeling. It's way, way cheaper. You can run hundreds of tests in a single day, and the only thing that can possibly explode is a bad line of code. This virtual lab lets us do the impossible.
We can simulate the very first microsecond of an explosion. We can model the airflow inside a single human lung. We can crash test a car without ever denting any metal, or simulate the immense forces inside a star. We can go to places and scales that are just completely off limits in the real world. But this is where our story takes a major turn.
Because that sentence, that scientific mantra we started with, it was never just about combustion. The source material was hiding a huge secret. That very same code, that same fundamental idea, is being used to simulate, well, pretty much everything.
Just check this out. That same modeling approach isn't just for engines. It's being used to model the growth of an entire economy. It can simulate things on a cosmic scale, from how gas clouds form between stars to how a dying star collapses on itself. And it works on the atomic level too, predicting how atoms cluster together in liquid metal or how plasma behaves inside a fusion reactor. It's mind-blowing. And this is the key insight. The same fundamental logic works across all these totally different fields. That repetition we saw at the beginning, it wasn't a mistake at all. It was the signature of a universal tool. The specific math might change a bit from topic to topic, but that core process, mathematical, numerical, algorithmic, it stays the same. Which brings us to the big idea here. We are not just looking at a clever technique. We are witnessing a fundamental revolution in how we do science, one that completely changes the questions we're even able to ask.
And this brings us full circle. That glitch we started with was the entire point. The repetition wasn't lazy, it was a sign of incredible efficiency. It shows that science has developed a foundational, universal method for tackling incredibly complex problems, all through simulation.
So what started out as a tool for engineering is now a universal toolkit for discovery. It lets us explore what-if scenarios on a cosmic scale, test in ideas that were once just confined to our imaginations. So whether you're studying the market, or materials, or the Milky Way, the language of simulation is becoming the language of science itself. And that leaves us with a pretty profound final thought. We've basically built a code that can model the cosmos. So the question isn't really, can we simulate something anymore? It's what should we simulate? Of all the huge challenges we face, where should we point this incredible engine next?